Hello, thank you for watching this video. So in this video, we'll be doing similarity of triangles. So we're done with proportionality. We're going to do similarity of triangles and then we're going to do Pythagoras afterwards. So what we're going to do, we're going to define similarity for triangles, right? And then do associated proofs and do some worked problems. So we're going to do some examples after all of this. But I assume I'm going to do it over 2 or 3 parts. I'm not sure how many parts I will need to get this over the line, because I'll have a few theorems to prove around and then of course define a few things. So let's go. So similarity of triangles. What does it mean when you're saying two triangles are similar? So if you're saying two triangles are similar, it means that those two triangles have the same shape but not necessarily the same size, right? So by that, I'm not saying the same shape in a sense of, okay, they are both triangles. If you are saying that they have the same shape in this case, I'm saying they're both triangles, of course, but those triangles, they look exactly the same. But of course, they might differ in size. I know that you can have an acute triangle or you can have a right triangle. They are both triangles, right? But those, they cannot be similar. So I'm not saying same shape in the sense of, okay, both triangles, both circles, or both squares. I'm saying we're both dealing with triangles, but those triangles, they look exactly the same. Not exactly, but they look the same, but they might be different in sizes. Or of course, they can be the same. Are you clear with that?
Yes.
So, for short, you can say, right, two triangles are similar if they have the same shape but not necessarily the same size. So, in this case, you're dealing with two triangles that look the same. They have the same shape, but they might be different in sizes. Or they might be the same size. They will still be similar. That's what it means. Or, you can say two triangles are similar if they are scale divisions of each other. So when I say they are scale divisions of each other, they are multiples of each other, which means you can move from triangle 1 to triangle 2 by multiplying all the sides with a certain vector. I'm not sure if that makes sense. So, this is, I'll say maybe this is definition number 2. So two triangles are similar if they are scaled versions of each other, right? Yes. Which means you have a triangle here. Let's call it A, B, C. So if this is a triangle A, B, C, in trigonometry we say this is small letter A, yes. This is small letter B, opposite B, and this is small letter C. Yes. Let's suppose that this triangle is multiplied by a factor K. So, where K is a real number, of course, a positive real number. Yes. So, we multiply all of the sides such that we get this triangle here. You can see that's a bigger version, right? So, let's call it maybe D, E, F. So, and assume that this side corresponds to this one corresponds to that one, and this one corresponds to that one. Which is this side is represented by that one, this side is represented by that one, and this one is represented by this one or the new one. Of course, if you look at it, this will be small letter F, right? Yes. This will be small letter D, and that will be small letter E. But to get F, we multiplied C by K. So your F is called KC. Yes. Right? Yes. To get E, you have to multiply this B by K. So your E is equal to KB. And your D is equal to KA. So you can see that this triangle DEF, the new triangle, is a multiple of this one. So to move from this one to that one, we had to multiply all the sides by factor K to get that. We multiplied all of them by some factor K to get that. I'm not sure if you're following. So in that case, if two triangles are scale divisions of each other, then those two triangles are similar. So in any case, let's suppose that K is equal to 1. Right? If your K is equal to 1, you should see that your DE will have the same length as AB.
Yes.
Because it will be 1 times C, which is just C.
Yes.
And your E will have the same length as B because it will be 1 times B.
Yes.
And your D will have the same length as your BC there. It will be 1 times A. So all the corresponding sides will be equal. So those two triangles will be congruent, which is they will be identical. You'll be looking at the same triangle but just labeled differently. But if your K is 1, so this one will be double that one. So if your K is 2, this new triangle will be double that one. Yes. If your K is 1, they will be identical.
Yes.
If your K is a half, this new triangle will be half of the original triangle. So if your two triangles are scale divisions of each other, like I've defined here, that all of the sides are multiple of some factor K, then those two triangles are similar. Right?
Yes.
Maybe this is the second definition. So I'm going to try the third one. The third one is the one that I think is very important in my opinion, and is what we're going to be using most of the time. So these ones, they just try to give you some sort of visual. This one is very vague. This one is getting somewhere. The next one is going to be more precise because it's what we're going to use mathematically to prove some stuff. So, third definition, I'll say two triangles are similar, right? If one, I'll write in conditions. Are you following me? Say all corresponding angles are equal. I'm not sure if you get this. Yes. And all corresponding sides are in proportion, which is they're at equal ratios. I'm not sure if you understand what I'm trying to say. So, two triangles are similar if all corresponding angles are equal and all corresponding sides are in proportion. What does it mean for corresponding sides to be in proportion? They are of the same ratios. So, I'm going to make an example. Let's look at triangle ABC, right? And triangle DEF. These two triangles over here that we have. These two triangles that we're reaching there. So look, if, according to this definition that I've used here, if triangle ABC is similar, these three vertical lines, yes, we use them to denote similar, is similar to triangle DEF, then here what you know, 1, which means the corresponding angles are equal. So the order in which you write these numbers, these alphabets, it means that your A in triangle ABC corresponds to D in triangle DEC. And your B corresponds to E in triangle DEF. And your C corresponds to F in triangle DEF. So the order in which you write these matters. Because if you write ABC is similar to triangle DEF, that's what I'm going to assume, that this angle is exactly the same as that one, This angle is exactly the same as this one, and this angle is the same as that one. If you swap them around, now you're talking about different stuff. Because that's what we said here. We said ABC is similar to triangle DEF, which is this angle here, according to that first condition. This angle A is equal to D, that B is equal to E, and C is equal to F. Right? That's what this means. You can see it here as well. Are you happy with that? So, according to this definition, if you're saying these two triangles are similar, that's what you need to know, that corresponding angles are going to be equal, which means your angle A is equal to angle D, your angle B is equal to what? Equal to angle E, and your angle C is equal to angle F. I'm not sure if you understand that.
Yes, I do understand.
That's the first condition. And, which is they both hold at the same time. And, what is it? All corresponding sides are in proportions, right? What are corresponding sides? We're saying, if you look at AB here, AB goes together with DE. So we will say that your AB, after it has been transformed by that scale factor K, it became DE. And your AB became DF, and your BC became EF. So, if you're saying the corresponding ratios are in proportions, which means if you take the ratio of AB to that of DE, it should be the same as if you take that of AC to DF, which should also be the same as that of BC to EF. I'm not sure if you understand what I'm trying to say. I'm trying to say to you, if you're saying triangle ABC is similar to triangle DEF, the corresponding or the ratio, the corresponding all corresponding sides are in proportion, which means your AB over your DE should be the same as your AC over your DF, which should be the same as BC over your EF. The order also matters. If you take a length from this side and divide it by its corresponding length on the side, you should be consistent, and all of those should be divided by this side. So you can't say your AB over DE is equal to DF over AB. Now you see, now on the first ratio you took the small triangle and divided by the big one. So you should be consistent and take the big one, the small one again from the other side and divide it from this side. Not sure if that does make sense.
Yeah, it does.
So you need to be consistent. It doesn't matter. You can even start here and say your DE over your AB is equal to your DF over your AC is equal to your EF over your BC. As long as you're consistent, start in one direction and go to the other. You can't mix them around and say this over that is equal to this over that. No, you can't do. You need to be consistent. You need to follow the same order. If it's this triangle, divide that one. Stick to that. If it's this one divided by that, move in that direction. Are you happy with that?
Yes.
So in this case, I said now, all corresponding sides are in proportion, which is the ratios of the corresponding sides are equal. Are you following that?
Yes.
So in this case, what you can see here on the diagram is also what you can see there. But what you should also keep in mind, these triangles can be upside down. Do you understand?
Yes.
So sometimes it might be difficult to say that A corresponds to D. But if you have this order in a correct way, then you'll be good. I'm not sure if you understand. If this order of alphabets is correct, you don't need to stress much about what happens in the diagram. Because the upside down diagram might be rotated, can be upside down, can be in weird positions. But as long as you have this correct order of alphabets, it's easy, because you know your angle A is angle D, your angle B, angle E, your angle C is F. So if you want now to see the corresponding sides, you are saying now, that order also works as well. So you take the alphabets as you see. You see the first two there is AB. Your AB here, which is the first two, will correspond to the first two there. That's why the order matters. So which means your side AB corresponds to the side DE, and your side BC corresponds to the side EF, and the side AC corresponds to the side DF. Do you want me to repeat that?
Yes.
I'm saying the side AB corresponds to DE, and the side BC corresponds to EF, and the side AC corresponds to DF.
Yes.
So, what I'm trying to say, if you're saying all corresponding sides are in proportion, which is they're at equal ratios, if I take the ratio of the corresponding sides, they should be equal. What am I saying? I'm saying at number 2, which is corresponding to this. I'm saying if you say your AB divided by its corresponding side DE, it is equal to your BC over EF, which is equal to what? Your AC over DF. I'm not sure if that does make sense.
Yes, it does.
It doesn't matter the order. You could have said your DE over your AB, say EF over your BC, or your DF over AC. It doesn't really matter. You can say the same thing here. So okay, now DE over AB is equal to what? EF over BC, which is equal to DF over AC. Over AC. Doesn't really matter which way you go, as long as you take the ratios of the same parts. Are you happy with this? Are you happy with this? So, this is the one that I like the most, which is this one. So I'll say two triangles are similar if all corresponding angles are equal and all corresponding sides are in proportion or are at equal ratios. I'm not sure if you understand what I'm trying to say.
Yes.
So, when you are doing this thing, most of the time, you'll be finding the length of sides, you'll be proving if two sides are similar in all those kind of things. Do you understand? So you'll be given numbers at times and you'll be expected to calculate sides. Sometimes you'll be asked to prove things. So with these three definitions, like I said, this one is the one that I like the most because at least it gives you ways of proving that two triangles are similar. Because look here, if you're saying they have the same shape but not necessarily the same size, what does that really mean? You know, so it's not very clear cut. But this one, we are saying they are scale versions of each other. Okay, this one you can work. So it's more like, by just at first glance, this one looks like it's a half of this one.
Yes.
But it's not a half, it's the same. But just that it chose to highlight only the second part of this one. Because if you look at it, we said that they are scaled versions of each other, which means if you take the ratio of the corresponding sides, they should be equal. So if they are scaled versions of each other, which means each of these sides are multiplied by some factor to get these ones. So if you take these ratios with these ones, you'll see that these ratios here, which is your, what is AB over DE, you'll see that it's going to be 1 over K. Do you see that?
Yes.
Same thing, so your BC over EF, what is BC? BC over EF, which is, it will be your A over your KA. So 1 over K.
Yes.
Same thing with that one. So, you might be asked now, if two triangles are similar, right? And the question that you might ask yourself is, how do you prove that two triangles are similar? So, with these three definitions, like I said, I'm going to focus on the last one, because this one makes it easy for us. So, you can say, okay, if you can show that all corresponding angles, which is show number 1, all corresponding angles are equal, and all corresponding sides are in proportion. That should be enough, right? Of course, because we will have proved both conditions.
Yes.
Which means we'll look at the given triangles, and look at the angles, and look at the ratios of the corresponding sides. Right?
Yes.
But the challenge with that is that What if you're only given angles but there are no sides? Then how do you check number 2? Do you see that?
Yes.
Or what if now you can see all the corresponding sides are equal, but you don't have the angles? Because look here, I said these are scaled versions of each other, right? Which means if you take these ratios, the ratio of this part to that part, this part, you see that they are all equal.
Yes.
But what about, so which means your number 2 will pass there. But what does it mean about number 1? Because you don't have the angles on the second definition. So now, this might be begging to ask, is number 2, since all of them are equal, does it mean, is it okay to say that if number 2 holds, this one will hold as well? Or if this one holds, that one will hold as well? Because now, at this second definition, we have a problem of number 1 where we cannot show number 1. Because we can show number 2 that it holds that all the corresponding ratios are equal. Because we said, if you say all these ones over those ones, so we said these ones will be 1 over k's, all of them, right? Yes. And these ones will be k's. Because if you say your DE over your AB, it will be your KF over your C, your KC over your C. So it will be C if you take it this way. All of these ratios here, they're equal to K, and these ones over here are equal to 1 over K. So now, is this enough to say these are similar when we need both conditions to be true for two triangles to be similar? So what I'm going to do right now is to answer that question. To answer the question, what we're going to show going forward is that if you want to prove that two triangles are similar, you don't have to prove both of those conditions. Being able to prove one will be enough to conclude that both triangles are similar. So if you can show all corresponding angles are equal, then we have enough to say that those triangles are similar. What does that mean? Which means number 2 as well will also hold. It is forced to hold. And we'll turn around also and show that if number 2 holds all the sides are equal proportions, then if all sides are in proportion, then those triangles should be equiangular. I'm not sure if that does make sense.
Yes.
That's what we'll be doing. So, before I even start, I'm saying that you don't have to show both conditions. Showing one would be enough. But we can't do that yet. We have to show that saying all corresponding angles are equal implies that your sides will be in proportion, and show that if all sides are in proportion, those angles, your triangles will be equiangular, which is they will all be equal angles, or their corresponding angles will be equal. That's what I'm going to prove. Then now, maybe I will loosen this definition. You understand?
Yes. I
will loosen this definition and stop saying that A and B, condition 1 and 2 must hold. I'll say 1 or 2. Which means 1 is enough and 2 will be enough as well. Because as it stands, it wants both of them to hold. But triangles are they are very understanding. So we are going to prove that if all the corresponding angles are equal, then the two triangles are going to be similar. Right? Yes. We'll show that if all corresponding angles are equal, then two triangles are going to be similar. So what does similar mean? Which is both of these conditions hold. I'm not sure if you get that.
Yes.
So I'm going to clean the board, and we are going to do the first theorem, which is to prove the first part. That if we have two equiangular triangles, or if we have equiangular triangles, those triangles are similar. Equiangular means triangles with equal corresponding angles. Are you happy? Yes. So let's clean the board and try to prove that theorem and see how that will go. Okay, so now we're doing our first theorem, and we've named this theorem equiangular triangles, right? So the reason I'm saying is equiangular triangles That will be the our reason when we quote or use this theorem, right?
Yes.
So here, what I'm trying to say, I'm trying to show the part one of those two conditions that I listed before. I said there on the third definition that was orange down here, I said that if we're saying two triangles are similar if all corresponding angles are equal, right?
Yes.
And all corresponding sides are in proportion, which means all the corresponding sides that they're at equal ratios, which is if you take the ratio of the corresponding sides, they're all going to be the same.
Yes. So
here, that's how I define similarity there, and I said that's the one that I'm going to use going forward. So in this case, I'm saying equiangular triangles are similar. What does it mean by similar? All corresponding angles are equal, and the ratio of the corresponding sides are also equal as well. That's what I mean by similar. It's that orange one. So if I'm saying to you now equiangular triangles are similar, I've given you that all the corresponding angles are equal.
Yes.
Can you see that?
Yes.
Which means now, to complete that definition down there, you must show that the sides of the corresponding sides are in proportion. That's the same thing. Are you following?
Yes.
Okay. So, in this case, we're saying equiangular triangles are similar. So, what do we want to prove? We want to prove, which is what we're about to prove. We want to prove that triangle ABC is similar to triangle what? DEF. That's what we want to prove. But to prove this, we need two conditions, right? Yes. The first one, all corresponding angles are equal. But we're already given this one. You can see it. Yes. So in order to complete the set for this, or complete the requirements to prove this, we must prove the second part now. Which is what? Which is to show that the ratio of the corresponding sides are also equal. I'm not sure if you understand that.
Yes.
So which means, what we want to show here essentially, that your AB over your DE is equal to your BC over your EF, which is equal to your AC over your DF. This is what we need to say. This is what we need to prove to complete this, the condition for this. Because to complete the condition for similarity, we must show that all the corresponding angles are equal, right? Which were given. Because these triangles, we're told that the triangles are equiangular, which is these triangles are at equal angles. They have equal corresponding angles, which is your angle A is equal to D, and your angle B is equal to E, and your angle C is equal to F. So we have the first one. The second condition that we need to prove to complete our requirements for similarity is this one over here. So this is what we need to prove in order to complete this. Are you following?
Yes.
Okay. So, which is, you must show that your AB or your DE is equal to your B, equal to your BC over your EF, which is equal to your AC over DF.
Yes.
That's what we need to do. So, this is what we know what we want to prove. But what are we given? What do we know? What are we given? Which is what we know. We know what we're told, that these two triangles are equiangular. Yes. What does it mean to be equiangular? Which means the corresponding angles are equal. Which is your angle A is equal to angle D. Your angle B is equal to your angle E. And your angle C equal to angle F. This is what we're given. Then now, we're going to construct now and get on with the proof. Now, let's go to construction. Construction. How are we going to do this? For our construction, so like we're going to draw this triangle inside here. We're going to take this triangle and kind of move it. Copy and paste this triangle inside here.
Yes.
I'm not sure you understand that.
Yes.
We're going to copy this triangle and put it inside here. Because the reason I'm saying copy and paste on top of this one, this angle are equal, right? Yes. So this angle this triangle will just overlie nicely here.
Yes.
I'm not sure if you understand what I'm trying to say. This triangle is going to sit nicely here, but it's not going to cover all of it. It's going to only cover for whatever the length of those things are. Yes. So what we're going to do, we're going to say, okay, we're taking this triangle, a copy of this, and paste it here. So when you paste it here, let's say this, can you see here? This part will sit here, and that part F will sit maybe there. Can you see? So let's say this is X, and this is Y over here. Can you see? And this one is equal to that, and this one is equal to that one. Can you see that these angles are equal? So it's going to sit nicely like here, like that here, or like this here. I follow you. And then after that, we're going to join these two. That's our construction. So let's go and write it down. We're going to say, let's mark X and Y on where? On AB, which is your X is marked on AB, and AC, which is your Y is marked on AC, respectively. Such that your AX, such that this length here is equal to that one. AX is equal to DE, and your AY is equal to DF. So what you're writing here is what you've done here, but you're not done. And then you're going to join what? Join XY. So what I'm writing here is what we've done there. So we've marked X on AB and Y on AC, such that your AX is equal to DF and your AY is equal to AX is equal to DE and your AY is equal to DF. So what you want to do, you want to get this ratio over here. Are you following that? So what I'm going to do, let me just give you a clear picture of what we're going to do. What we're going to do, look, this triangle and this triangle, if you look at them, it's the same triangle. Because it's a copy and paste if you look at it. But if you're not happy with the copy and paste, this side is equal to this side. This angle is equal to this angle, and this angle, this side AY is equal to that side DF. Which is your AX is equal to DE, your AY is equal to DF, and your angle A is equal to angle D. So these two triangles are congruent. If they're congruent, this angle here is equal to this angle here. And this angle here is equal to that angle there. Are you following?
Yes.
Which is these two angles will also be equal.
Yes.
Are you following that?
Yes.
Are you following that?
Yes.
These two angles will also be what? Will also be equal. Which means if these two angles are equal, these two lines are what? Are parallel. And you apply your proportionality theorem going there forward. Are you following that? And say, okay, our which is our AB over AX is equal to AC over AY. That's your proportionality theorem from the previous classes.
Yes.
But you know that AX and AY equal to DE and DF respectively. Yes. Which means you have proved that your AB over ADE is equal to AC over your DF.
Yes.
Which is you've done this part. And then go to the second part. But most of the time when they ask you, they only ask maybe half of, not half, maybe 1/3 of this part. They don't ask the other part.
Okay.
So they'll only ask you to prove this part. That's why your proof would normally end in an exam. But we're going to do all of it so that you understand. And because we have joined these two sides, AB and AC, the ratio that we're going to get out of this will include AB and AC, which means it will be these two parts.
Yes.
But if you want a ratio that will include your AC and your BC, you must make a similar construction but joining now these two sides.
Yes.
So this line joining this must join here. Now you get a ratio that will connect these two. If you want a ratio that will connect your AB and your BC, it should be a triangle like that.
Yes.
And that triangle should be a copy and paste of this one, which means this angle must overlie there perfectly. Same story. But let's continue with what we're doing. So we're going to start with our proof now. Our proof. Are you happy?
Yes.
So I'm going to say in triangle AXY and triangle what? DEF. Do you see the two triangles?
Yes.
I'm going to say our AX, which is AX over there, is equal to DE. How are these equal? Because of our construction. We've constructed our AX so that it is equal to that.
Yes.
By construction. Are you happy?
Yes.
I'm going to say now,
AY.
angle A is equal to what?
FD.
Angle D. Because the common angle. Oh, we're given actually. Angle A is equal to angle D. We're given.
Yes.
This was given information. And this one, it was part of the construction they did.
Yes.
So this was given. Then we're going to say AY is equal to what?
DF.
It's equal to DF. What is the reason? AY is equal to DF. It's a what?
It's a construction.
Construction. So this is by construction. If you look at these two triangles are congruent. Because okay. Therefore, triangle what? AXY is congruent to triangle DEF by side, angle, side. What does it mean for two triangles to be congruent? It means they're identical. It's the exact same triangle. Like I said, because we said it's copy and paste of it over there.
Yes.
So they're the exact same triangles. Do you understand?
Yes.
Okay. So they're identical. So if they're identical, if these two are identical, this angle here is called to this angle, this side is called to the side, this side is called to the side, this angle here is called to that angle there, and this angle here is called to that angle over there. So which means this angle here, let's say maybe it's x1, x2, y1, maybe y2, I don't know. So this angle as well should be equal to that. Because it's the same position of it's the same triangle. So your angle x1, you can say from this, your angle x1, this angle here is called to this angle E here. The angle x1 is called to angle E. These are corresponding angles of congruent triangles. This is a triangle here. What does this mean? When I'm saying corresponding angles of congruent triangle, I'm saying it's the same angle of identical triangles. Because we say these two angles are identical. So this is the same angles of these identical triangles. If you don't understand it, you can go back on my videos. I did congruence when I started. Are you happy?
Yes.
Okay. So which means, now, your angle E is equal to x1.
Yes.
And your angle B is also called to E.
Yes.
We're given this, here is it.
Yes.
So which means, your angle B is called angle E. What does it mean about these two?
They're also equal.
So if E is equal to E, so your x1 is equal to angle B. Which is these two angles are equal.
Yes.
And if these two angles are equal, so you have two lines, right? XY and BC, intersecting a third line at the exact same angle.
Yes.
What does it mean about these two lines?
They are parallel.
They are parallel. If you have two lines intersecting a third line at an identical angle, which is your corresponding angles are equal there, those two lines are parallel. So in this case, you say, okay, therefore, what?
XY.
XY
It's parallel to BC.
parallel to BC. Why? Because of the corresponding angles that are equal. We did this. If you don't understand it, go back to my videos. You will find this. I did this. So, what do we do now? In this case, we just found that this is parallel to that. Are you happy?
Yes.
We did the proportionality theorem. So we can apply the proportionality theorem.
Yes.
Because look here, we have AB over DE, which is the big part over the small part.
Yes.
Which is a big part over the smaller part over there.
Yes.
But if you look in triangle AXY and triangle ABC, because these two are parallel, we're going to apply the proportionality theorem.
Yes.
And say that AB over AX is equal to AC over A1.
Yes.
So we're going to say, okay, which triangle are we working with? In triangle
ABC.
ABC. And triangle what?
AXY.
In triangle AXY. So we're going to say AB
over AX.
over AX equals what? AC over AY. This is the proportion. We're applying the proportionality theorem.
Yes.
We did this in the previous video.
X
Because
is
XY
parallel to BC.
is parallel to BC. That's why it works. So what we have here said AB over AX called AC over AY. We're applying the proportionality theorem.
Yes.
After I proved the proportionality theorem on the previous videos, I did a lot of these ratios, which I said were equal.
Yes.
Same thing. I'm applying one of those ratios. That's why I did them, so that when I'm applying them now, you don't say you don't know them. I didn't want you to only know that AX over XB. I did all of them.
Yes.
So that we would not have problems when we get here. In this case, now, remember that AX is equal to what? It's equal to DE. And your AY is equal to DF. Which means what you have here is what? Is AB over DE equal to AC over DF. This is where you normally stop with the proof, because this is what you have there from construction. Because you're saying this is equal to this, and this is equal to that. Which is, what you've proven is this first part there. Not first part. You have proven this part. That this is equal to that one. Right?
Yes.
Now, to prove this now, the third one, what do? Do the same thing you did on the first one, in the first construction. Copy and paste this. Let's copy this one and paste it down here. Let's put this F on this C over here. Here, copy as is. This point D, let's say maybe somewhere here. Right?
Yes.
And call it maybe P. And then your E will sit somewhere here. And call it maybe Q. And then you join these. So this P is such that PC is equal to that. And your EF is equal to QC. Does it make sense?
Yes.
So you copy this as is and put it down here. This Q, this F is sitting down here.
Yes.
So, and then try to align other sides. You see it will be something similar to this.
Yes.
We're going to do the same thing. We'll prove that these two triangles are congruent. You can see that they're congruent.
Yes.
By side, angle, side.
Yes.
Right?
Yes.
This angle here is equal to that angle.
Yes.
And that angle is equal to this angle.
Yes.
So, which means these two sides are parallel.
Yes.
Because the corresponding angles are equal.
Yes.
You take the same ratio, same thing. So I'm going to do it, but I'm not going to do it as clear because it's the same thing. It's the same proof. So what I'm going to say, what do I get here? Normally, they will ask you to stop here. So I'm going to say more construction. Right?
Yes.
I'm going to mark P
Q
and Q on what? On AC
and BC
and BC respectively.
Such that
Such that what? Your PC is equal to DF
F
and
and
QC is equal to
EF.
EF. Are you happy with that?
Yes.
If you do that, continue and say, you will see that triangle PQC is congruent to triangle DEF by side, angle, side. Same stuff as this.
Yes.
You understand?
Yes.
Therefore, if you say this is maybe P1 and P2, Q1 and Q2, you'll see that your angle P corresponds to angle D.
Yes.
So this angle P1 of yours is angle D.
Yes.
So say angle P1 is equal to angle D. These are corresponding angles of congruent triangles. I follow you?
Yes.
But your angle D is called angle A. Your angle A is also called angle D.
Yes.
So these two are equal.
Yes.
Which is these two are also equal as well. Therefore your P1
Also angle A.
is called angle A. These are, you don't have a reason for this. This is the transitivity of equality. You don't have to reason for it. In that case, if this angle and that angle are equal, as you say there, which means these two lines are parallel. Because we have two lines intersecting a paired line AC at the exact same angle, which means your PQ is parallel to AB. What is it? It's PQ.
It's PQ parallel
PQ
to AB.
is parallel to
AB.
AB. Why? Because the corresponding angles are equal. So say in triangle PQC and triangle ABC. Can you see? Triangle PQC and triangle ABC. Can you see that?
Yes.
So you can say that your AC over PC is equal to BQ is equal to BC over QC. Are you happy?
Yes.
These are, we apply the proportionality theorem here.
Yes.
Why? Because our PQ is parallel to AB. Are you happy?
Yes.
But look now, PQ, PC
PC
is equal to what by our construction?
PC
Is equal to DF.
is equal to DF
And our QC is equal to EF. So what we have here is AC over what? Over DF equaling what? BC over QC. What is your QC?
QC is EF.
QC is EF. So what you have, look now, what you have here, you have your AC over DF equal to BC over here. Your AC over DF equal to your BC over EF. Look here, your AC over DF is equal to this. And the same AC over DF is equal to this. So all of these three things are equal.
Yes.
Because look, your AC at 1, let's say this is equation 1, and this is equation 2. So which means your AC over DF is equal to AB over DE.
Yes.
And the same AC over DF is equal to BC over this.
Yes.
So all of these three things are equal. So in closing, I'll say your AC, actually, let me write it as is there. Let's say AB over DE is equal to AC over DF. Look at this AC over DF is also equal to BC over EF. So we should have shown all three of them. Are you happy?
Yes.
The reason I didn't stop here where they normally stop is because if you stop there, it would be easy for a student to assume that if two ratios, if two sides, if two corresponding sides, if two pairs of sides are in proportion, then the two triangles are similar. I'm not sure if you understand what I'm trying to say.
Yes.
So I continued up until the very end to show that all of them, they should be in proportion for you to consider them similar. So I'm proving the whole thing holistically, all of it. I don't want to prove half of it, so that you think, if you can see that, if you see two triangles and see that, okay, the two pairs are in proportion, and then you assume that everything else, then those two triangles are similar. I don't want you to think of that, because that might not be enough. As I will show down the line, that it's not enough for two triangles to be similar. All of the sides should be in proportion. So the ratio of the corresponding sides should be equal. So I'm done with the first theorem. I'm not sure if you have any questions for me.
No questions.
You understand it?
Yes.
You'll know it when I want it.
Yes.
Okay. Then we're good then. Then now, I'm done with this proof. But I want to talk about something related to this proof. So what this says to you, actually, we should have maybe concluded that therefore, triangle, what? Maybe we should have concluded and say, therefore, triangle ABC is similar to triangle DEF. Because both conditions are now met, because you have the corresponding ratios all being equal, and the corresponding the corresponding ratios, yes, are all being equal, and the corresponding angles are also equal. I'm not sure if that makes sense.
Yes. It does make sense.
All the ratios are in proportion, and all the corresponding angles are equal. So we are safe to say these two triangles are similar. So what I want to talk about now is, which means if you show that two triangles are equiangular, if you can show me that two triangles are equiangular, you can assume that those two triangles are similar, and you can use those ratios as you want. So if you want to show me that two triangles are similar using the equiangular method, which means you think that you have to show all three of them, right?
Yes.
In honesty, you don't need to show all three of them. Showing just two pairs will do the work. If you can show me these two are equal, these two angles are equal, and these two are equal, that one will also follow automatically. If you show me that these two pairs are also equal, that one will also follow. So you do not have to show all three. You can if you have time and you want to. Just show me any two pairs of corresponding angles that are equal. That should be fine. Not sure if that makes sense. So what I'm going to do now is to show you that if you have two triangles and two corresponding angles are equal, those two triangles should be similar. Because all of those angles in those two triangles, they will be equiangular, and we just prove that equiangular triangles are similar. Do you understand?
Yes.
So I'm going to clean the board and then extend that just to show that if you want to show two triangles are similar by using angles, you don't have to show all three pairs. Just two pairs will do the work. But if you want to flex, you can show all three pairs. So let's clean the board and emphasize that if two pairs in two triangles are equal, if two pairs of angles in two triangles are equal, then those two triangles are similar. So let's clean the board and we'll do it. Okay, so I'm going to prove this, and then after that I think I'm going to wrap the class because we're nearly an hour in. So this is an addition to the previous theorem, right? In the previous theorem we said equiangular triangles are similar. Are you following that?
Yes.
So we said that if you are given two triangles and the corresponding angles of those, all the corresponding angles of those two triangles are equal, then the sides will be in proportion, or the ratios of the corresponding sides are going to be equal. Are you following?
Yes.
So I said that now, if you can show me that, if you're given two triangles and you can show me that all the corresponding angles are going to be equal, right?
Yes.
Then what you need to know is that those triangles are similar. Are you following?
Yes.
So what I was saying essentially is that to show that two triangles are similar, show that all the corresponding angles are equal. So what I'm going to show you here is that you don't have to show all three pairs of corresponding angles. Showing two will be enough because the third one will also follow automatically. So triangles with two equal pairs of angles are similar. If you have triangle ABC and triangle DEF, and you know that angle D is equal to A and this angle E is equal to B, then these two triangles are going to be similar because this angle as well will be 180 minus the sum of those two. Do you understand?
Yes, I understand.
I'm saying if you have a situation like this and you can show me that A is equal to D and B is equal to E, then your triangle ABC and your triangle DEF are going to be similar or are similar. Why am I saying this? I'm saying this because this angle as well will also be equal to this one. Because this angle here is 180 minus that angle minus that angle. Which is the same here, 180 minus this angle minus that angle. So which is this angle, that angle are equal. Which means that these two triangles are going to be similar as well. Because they will be equiangular in that case. Are you sure? So essentially, if you have a case like this, these two triangles are equiangular, which we just prove that they are similar. So let's just prove it. Because okay, this is our proof right now. You know that if you say A plus B plus angle C, what do you get?
180.
180 degrees.
Angles on a straight line.
Duh. Are you sure?
Side angles.
And then now, look, If you say angle D plus angle E plus angle F equal to 180 degrees. Why?
Some angles in a straight line. I know, so some angles in a triangle.
Yeah, depart.
No.
In that case, 180 is equal to 180, right? Which is the right hand side equal to the right hand side. So are the left hand side. Which means your
A
plus B
plus C
plus C. Angle C is equal to angle D plus angle E plus angle F. Are you happy with this?
Yes, I'm happy.
But remember, your A is equal to
A
angle
is
D.
equal to angle D.
This was given. And
Angle B
your angle B is equal to
angle E.
angle E.
We given that.
This was given. What does this mean? Which means here we can put D, angle D, right? Because A is equal to D. And here we can put angle E
Plus angle C
plus angle C to be equal to angle D plus angle E plus angle F. So this and that will cancel, this and this will cancel. So we're left with angle C,
was equal to angle F.
angle F. So what do you have? You have that A is equal to D, which is this equal to this. You have B is equal to E, which is this equal to this. Now we've just shown that your C is equal to F.
Yes.
Are you following?
Yes.
So what does that mean? It means that these two triangles are equiangular. Therefore, they are similar. You say therefore, triangle ABC is similar to triangle DEF. Why? We have equiangular triangles. So if you want to show me that two triangles are similar using angles, just show me two equal pairs between the two triangles. Then I'll be fine. Because if you have two equal pairs in two triangles, that means that those two triangles will be equiangular. And we just proved on the first theorem, on theorem equiangular, that equiangular triangles are similar. So if you have this situation, these two triangles will be similar. So I don't want you to waste your time proving all three triangles through all three angles. Just prove two and you'll be fine. Are you happy?
Yes, happy.
Yeah, and I hope this does make sense to you as it does to me. So on the next video, we'll continue with the converse of equiangular triangle. So now we've given that all sides are in proportions. You must show that they are equiangular. Does this make sense?
Yes, it does.
Yeah, so I hope it does make sense to you as it does to us. Thank you for watching the video. Cheers.